So, hey there everyone and welcome to part 4. Okay, so let's start. I'm also very sorry for the delays. It's because of rain and I have pretty bad internet connection. So just deal with it a bit. Okay, so we'll be starting with packing efficiency. So basically what is packing efficiency, right? Packing efficiency is the percentage of the total space filled by the particles. Okay, so how much space is filled by this particles in a specific place? That is what packing efficiency is simply put. So now, packing efficiency in HCP and CCP structures, both types of close packing are equally efficient. Okay, so here we are given this. So here A is given as edge length and B is the face diagonal. That's like AC. Yep, this is the face diagonal right here, like this, right? In triangle ABC, AC square equals to BC square plus AB square. So by Pythagoras, to find the length of this with this, alright? It's self-explanatory only. Okay, then B square equals to A square plus C square. So B is equal to root 2A. Okay, B equal to root 2A. This will be important. So here basically we get the radius of the sphere. That will be A by 2 root 2. Okay, it is A by 2 root 2. Then next up we look at the number of atoms in each unit cell of CCP. So in each unit cell of CCP we have 4 atoms, you already know that. So the total volume of all these 4 spheres, total volume will be 4 by 3 pi r cube into 4. So that will be 16 by 3 pi r cube into r we have given it as a by 2 root 2. So eventually we will get root 2 r cube. Because of the math, just do the math, it all gets cancelled. We might do it, alright? So we'll be looking at the packing efficiency. So here we got the volume. Now for packing efficiency, it is volume occupied by the spheres upon the total volume. So this is the total volume of the cube, and the volume occupied by the spheres is this 4 into 4 by 3 pi r cube, right? So here we have, this is the total volume, 4 spheres, and this is the volume of the cube. So eventually we end up with 74% as the packing efficiency. Now we will be seeing the packing efficiency in VCC. Okay, so in this, the atom at the center will be in touch with the other 2 atoms which are diagonally attached. So this atom touching this atom, so the 3 are touching each other. So by that we will be getting triangles. One is E, F and P. So this one. We also got A and B. So it's this one. Yep, that's self-explanatory pretty much. So F and B. This is sort of a diagonal middle of the cube. So F, A, right here. See that? See how it is. Okay. So the length of the body diagonal C is 4R. So this body diagonal itself like this 4R. R is the radius of the sphere. So we know. So A 4R, right? So in short we get a radius as root 3 by 4A. So in short we are replacing as R. We are replacing R by A. So we will be substituting here. So, C is equal to, so C and B will be obviously different, but C is equal to root 3 and B also is equal to 4R. So that's how we ended up on the conclusion R equal to 3 by 4A. Now we'll be looking at the total number of atoms per unit cell of GCC. So that is 2. How 2? This, that makes up 1, and this is this here, yes, that makes up as 2. So now next up we'll be looking at the volume of the cube. This volume will R by 3 cube. Yes. Now the packing efficiency. So basically, the volume by the two spheres will be 2 into 4 by 3 pi r cube. So one sphere here, it's 1, 3, 4, 5, 6, 7, 8 alpha. That makes up like two spheres, yeah, coordination. Okay. Not the coordination, but matrix. That is 2 over here. So basically, we get 8 by 3 pi r cube over pi root 3 r cube. So basically, we end up with 68% is the packing efficiency, and here we got it as 72 by 74. So we can say that HCP and CCP are more packing efficient. That's what BCC. Okay, now we will calculation involving the cell dimensions. So we do the volume of mass Z equals to M by Na. M is the molar mass. Okay, and we do that for the density. So here I have a bunch of questions which you can attempt. After this, we'll probably be looking at the defects while we scrolling whether to get them. Alright, so here we go. Now we will be looking at the imperfections in the solid. One more thing at the end of this part, I guess part 4 or part 5 probably, I will be giving you guys a bunch of questions, objective questions, which you can do very easily. Okay, so it will just be here because I really cannot share it in the description due to copyright issues. So make sure you check it out. So imperfections in solids. So in solids, any deviation from the perfectly ordered arrangement of constituent particles in a crystal is called a defect. A defect is an imperfection in a solid. Pretty self-explanatory. Okay, so right over here we have a point and line defect. So this first of all, the deviation from ideal arrangement around the point in a crystalline substance is called its point defect. Okay. So I guess I'll just show you guys the NCRT 1 second, please. This one. Yep, here we go. Okay, so first of all here we have this imperfections in solids. Now under this we have point defects and we also have line defects. So here we know that point defects are irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance. Okay? While line defects are irregularities of entire rows of lattice points. Okay, so you understood that point defects is like around an atom, around a point or an atom, but line defects is in the entire rows of lattice points. So these irregularities are also called as crystal defects, and we shall confine our discussion to point defects only. Okay, so here we have types of point defects. Under that, first of all, we have stoichiometric, we have impurity, and we have non-stoichiometric defects. Alright, back here. So under this, the stoichiometric, we have vacancy and interstitial. Under impurity defects, we just have impurity, and under non-stoichiometric, we have metal excess and metal deficiency. Okay, so the stoichiometric, first of all, we have these are point defects that do not disturb the stoichiometry of a solid. They are also called as intrinsic or thermodynamic defect.